Okay, so we have not too much left for the thermodynamics discussion. So today we're going to talk about vapor-liquid equilibrium. We covered gas-liquid equilibrium. And the main thing that we talked about was how much of the volatile substance, right, the subcritical fluid, will evaporate into the gas phase, right? So this could be benzene and air, it could be water and air, right? We use the term humidity anytime it's water and air. We use the term saturation if it's some other mixture. We talked about how much of the gas can dissolve in the liquid, right? And that's going to be using Henry's constant, which is a similar approach. So let me just write this out here. So we have our Raoult's law, right? And I'll write the T here just to remind us that the vapor pressure is a strong function of temperature. It's actually an exponential function of temperature, and that's information provided by the Clapeyron or the Clausius-Clapeyron equation. What is Y corresponding to in this formula? Vapor mole fraction, P, total system pressure, X, liquid mole fraction, and then Pi star, vapor pressure or saturation pressure, and then T to remind us that there is pressure and temperature involved in this expression. Right, so we're going to use this for liquid vapor or liquid in gas, right? This is going to be our humidity. So when we apply a simplification, we will assume that the amount of gas that dissolves in the liquid is 0. So that means that Xi essentially turns into 1 if this is for the liquid. So then we can easily solve for the mole fraction in the vapor phase. So for example, in the homework that we have this week, there's a problem where it's asking you how long it'll take to dry your clothes if the air in your dryer is a certain temperature and is fully saturated. Right? The warmer you make that air, the higher the vapor pressure is, such that the mole fraction of water will be equal to water's vapor pressure divided by the system pressure. So if I increase the temperature of my air in the dryer, I raise the vapor pressure of water. If I raise the vapor pressure of water at 1 atmosphere pressure, I will increase the mole fraction of water. Right? So now we have an optimization problem. We also talked a little bit about gas in liquid. Right? So for this problem, we just replace the vapor pressure with something called the Henry's constant from Henry's law. Yes?
Sorry, when did we assume that Xi is 1?
So if we have, let's say, air plus water, right? Air is a supercritical fluid. It doesn't want to necessarily be dissolved in the liquid. So in the case of Henry's law, we actually do care. So this would be used for if you're doing a bioreactor and you need to make sure you're providing sufficient gas resources like oxygen, right? Or you don't want to have too much CO2 buildup in your solution, right? This case here, Henry's law would take care of the really small amounts of gas. So these Henry law constants are really, really big, so that when you solve for Xi, it has to be really, really small, right? It's sort of the effective vapor pressure of a hypothetical liquid oxygen, for example. But in this case here, if we're trying to solve for how much water is in the air phase, we can actually neglect this small amount of oxygen or air that's dissolved in the water. So in this case here, we'll set that the X of air is approximately equal to 0, so that the mole fraction of liquid water is approximately 1. And then we no longer have to solve this as a system of equations. So today we're going to talk about solving this as a system of equations if we have a mixture like benzene, toluene. Both of those are subcritical fluids, but they have different volatilities. Or you could do gasoline and diesel, even though it's very complicated because it's a multi-component system. Okay, so this is a recap of how we got here. So this here is an approximation that we can use when we don't care about how much of the liquid goes in and when it's really, really small. But today we're going to be talking about vapor and liquid equilibrium, which is going to be slightly more complicated. So I'll start off algebraically. So let's just come up with a hypothetical example of, let's do benzene and toluene. So benzene is, of course, our aromatic compound. Toluene is almost the same, but it has a methyl group attached. Which of these two compounds is more volatile? First off, what does volatile mean? Which does it mean if a fluid is more volatile? Right? A volatile compound wants to readily evaporate. Now, is there a term I have on this board that quantifies volatility?
It has a low vapor pressure.
Opposite, the high vapor pressure. So a highly volatile compound wants to evaporate, wants to go into the atmosphere, right? So the term volatile is usually something that we think of having negative connotations with, right? Because if you're working with it, if more of it evaporates, you breathe in more of it, it's going to be more harmful. So that's why in labs we have fume hoods, which suck air in and then vent that volatility out so you don't have to breathe it. So if you're ever working with organic compounds, especially organic compounds that are hazardous and highly volatile, you must work with them inside of a fume hood, otherwise you will have a bad life. Okay? So benzene and toluene. Benzene is going to have a higher vapor pressure because it's going to be more volatile. Why do I think that benzene has a higher vapor pressure? I mean, I work with these two chemicals a lot, so I know. But what about their chemical structure makes it seem like it's going to be that this one's less volatile, this one's more? Yes, Ethan?
Toluene have a slightly dipole-dipole interaction between its molecules.
So it will have a slight dipole here, right? Because the methyl group with the aromatic carbon is not necessarily going to have exactly the same environment, but we also have just more atoms interacting, right? So even if this methyl-methyl carbon interaction isn't the strongest in the world, because we know it's not super strong, because methane is a gas, but the more molecules you add, the less and less volatile it's going to be as a general rule. So methane, supercritical gas. Ethane, supercritical gas. Propane, at room temperature, is propane supercritical or subcritical? Subcritical. Why is it subcritical? How do we know that?
Does it completely evaporate?
Can we buy propane? How do we buy our propane?
In liquid form.
In liquid form in those big drums. So those drums are pressurized. So if we can make it turn into a liquid at that temperature, then we know it's subcritical because we have liquid propane. Okay, butane. Who here has used butane? What do you use it in? Right? What fuel do we burn when we go camping? It's usually a mixture of isobutane and butane. Right? Isobutane is actually a little bit more volatile than butane because the T-shaped geometry of the isobutane makes it so that it's harder for the molecules to pack together. So when it's really cold or up high in the mountains, you'll actually get some pressure pushing that fuel out into your camping stove. Right? Once we get to hexane or pentane, those are liquid at room temperatures. Then we get up to decane, which is basically kind of like diesel fuel. So for example, in the exam, the fuel that you were burning was just decane. I just took the properties of decane and called it diesel fuel for the purposes of that problem. Okay, so if I want to know what happens when I mix these two together, right, and I want to know the composition of the liquid phase and the composition of the vapor phase, I have to apply Raoult's law and material balances. So in a general flash separator, okay, so this is going to be a flash separator. Okay, this is the most straightforward example. Now, not all of the problems that you'll see in this class are going to be the same straightforward example. What we're going to do is we're going to fix the temperature and pressure of this flash separator. We're going to know, and I write Z, meaning the total composition. Right? So Z, B, and Z of T, this is going to be the mole fraction of benzene and toluene of the total system. So it's feeding into it. So we can think of this like a batch or a flowing system, the same idea. So the feed is the total amount. We could also write this as NB feed and NT feed. In general, we're going to set that the flow rate of the feed is equal to 1 mole per unit time, or 1 mole, right? So it could be 1 mole per second, 1 mole per hour, or we could think of this as a closed system and just have it 1 mole, right? The difference between a closed system and a flowing system is just we have this time thing on the bottom. Okay, so there's a lot of different ways we can write the nomenclature. But in general, I'm going to assume that the basis being fed is 1 mole just because it makes our life a little bit easier. Okay, so we're feeding in a fluid with a certain composition of benzene and a certain composition of toluene. So we're going to know all of this. What's going to be unknown is how much is flowing out of my top stream. So that's going to be NT, that's the top stream. And this is going to be the bottom stream. In a lot of thermodynamic texts, this will also be called just V, and this will be called L. Right? So different nomenclatures, but they all have the same idea. But to keep the nomenclature consistent, I'll generally stick to NT and NB. Okay, so we want to know if I feed in a mixture of 2 compounds at some temperature and pressure, how much is going to go to the vapor phase, how much is going to go to the liquid phase, and then also what is the composition of those 2 phases. So it's going to be Y of benzene, Y of toluene. Right? Remember, the Y corresponds to the vapor, so I don't necessarily have to write Y top. Right? And then mole fraction of benzene and toluene in the liquid phase. So that leaves us with 6 unknowns. So our unknowns are the total amount of vapor in the top stream, the total amount of liquid in the bottom stream, the composition of the vapor, and the composition of the liquid. So if I have 6 unknowns, how many equations must I have? 6. So where do I get my equations from?
Mass balance.
Okay, mass balance or mole balance. So we have balances. This gives us 2 equations. Right? We get 1 equation for each independent species. I could choose a toluene balance, I could choose a benzene balance, or I could choose the total balance. Which one do you choose? It's dependent upon the problem. I generally like to use 1 species balance and 1 total balance. It makes the math a little easier. Yes?
Sorry, is that balance 2 equations or balance?
2 equations. Okay, what are 2 other sources of equations?
Physical constraints on the mole fraction.
Yep. So we get 2 equations from summation of the mole fractions in the liquid phase equal to 1, summation of the mole fractions of the vapor phase equals to 1. And that's generally what we've done so far. What are the final 2 equations? Raoult's law. So we are also going to have Y of benzene times the system pressure is equal to the mole fraction of benzene in the liquid phase multiplied by benzene's vapor pressure and mole fraction of toluene in the vapor phase, mole fraction of toluene in liquid phase multiplied by toluene's vapor pressure. So now what we have here is a way that I can give you a problem that is more realistic, because instead of me just telling you what the outlet compositions are, so for example, when I write homework problems or exam problems, I actually have to choose components or make up properties to solve for what the outlet compositions are going to be, and then I tell you those compositions. Now I don't have to do that anymore. I can just say, hey, the temperature and pressure are some value, and I just have to confirm that I'm in the two-phase region, right? And then you can solve for the rest of it now. So we're getting closer and closer to the real-world scenario. Okay. So what I can solve for now is that all of these equations contain my unknowns, 6 equations, 6 unknowns. I'm not going to tell you how to solve this. I want you to all go through, and when you have these flash calculations, figure out a way that works best for you. You will have to solve this oodles of times from now until the end of class, right? 6 equations, 6 unknowns, not too bad. Because there may be circumstances where I tell you what the total flow rate of the top stream is and ask you to solve for the pressure. If you remember how to do it algorithmically for one type of scenario, well, then you'd have to remember a new algorithm to solve it a different way. On the homework, I say, I'll solve for the temperature now. Well, that makes this nonlinear system of equations because the temperature is a nonlinear aspect of the vapor pressure, right? So it's not going to be super obvious which way to solve these, but being comfortable manipulating these equations is going to be the key to success, right? 6 equations, 6 unknowns. Depending on the situation, you're going to have to try a different strategy. Makes sense. Now, there is a way that I can take this example and I can turn it into a plot that contains all of the possible scenarios, right? So if I feed this at 50-50 at a temperature of 95 degrees at 1 atmosphere, I know that's in the two-phase region because I know the boiling point here is about 80 and here is about 100, right? So if I feed this, I will have benzene that wants to be 100% vapor and liquid toluene that wants to be 100% liquid. But when I mix them together, some of the benzene will dissolve in the liquid toluene, and some of the liquid toluene will evaporate into the vapor phase benzene. Right? So that's what we get vapor-liquid equilibrium. Same reason why if I take a cup of water and I put it in this room, the reason why the water evaporates is because it's not a one-component system. There's air and water. So once we have a multi-component system, we get a little bit more complicated thermodynamics occurring. So if I were to set that one scenario up, 50-50 mixture, 95 degrees Celsius, 1 atmosphere pressure, I would be able to solve for how much is evaporated into the vapor phase, how much is in the liquid phase, what's the composition of the vapor phase, what's the composition of the liquid phase. Right? That's just going to be one scenario though. What if I made this 40-60? 30-70, 20-80, 10-90, right? That's a lot of different scenarios. So a phase diagram contains all of that information. So a phase diagram contains all of the possible flash scenarios in one figure. The phase diagrams that I'm going to be demonstrating here were put together by Gibbs, right? A really famous thermodynamics researcher from about 100, 150 years ago. Right? So Gibbs thought that this would be a great way to plot the data, and most people seem to agree. So this is all based on Gibbs. Williard Gibbs, I think. Okay, so the first one I'm going to plot here is called a PXY phase diagram. Okay, so what this means is that the temperature is constant. So this whole diagram is made at a constant temperature, but I'm only varying the pressure. So I'm going to draw it out big because I'm going to annotate a lot of different parts of it. Okay, it's generally going to be some sort of a square box, but it can take different shapes. We're going to be looking at a lot of different phase diagrams. On the x-axis, I'm going to put Z of A. Right? This is the total composition of this mixture. And this is generally going to be useful for 2-component systems. 3-component systems, you have to get to a little bit more complicated phase diagrams. So A, and this is convention only, and it makes the phase diagrams look a little similar. By convention, A is the more volatile species. So in the case of the benzene toluene example, this would be benzene. Okay? So on the x-axis, I will plot out the composition of the more volatile species. And that just makes things look a little bit nicer. Okay. On the y-axis, I'm going to have the system pressure. Yes?
So we're talking about more volatile. You said like in general, we can use like the more atoms be. But what would be like a rigorous way to think about like which exactly one would be?
Using Anton's equation to figure out what the vapor pressure is. So the vapor pressure in Anton's is an experimentally measured value that they then fit to that equation. So another good way is when you go into the back of your book, either for this class or your thermodynamics class, in your Anton's equation table, right, you'll have the A, B, and C parameters. You'll also have the normal boiling point. That's another way. So a fluid with a high normal boiling point is low volatility. A fluid with a low boiling point has a high volatility. So like acetone boils at around, I think like 50 degrees C or something like that, right? Water boils at 100. But those two lines can actually cross each other depending on where the critical points are. So some fluids will have a high critical point, meaning that their vapor pressure doesn't change much over temperature. Some fluids have a low critical point, which means their vapor pressure changes a lot. So it is possible for at one temperature, one species to be more volatile, and then at a different temperature, the other species more volatile. Again, nothing super easy in thermodynamics. Okay, so when I approach a phase diagram, it helps me out a lot to think about the limiting cases. So if I have a mixture, let's say this is the benzene toluene mixture, and I have it at an extremely high pressure, 1,000,000 atmospheres, am I going to be in the gas phase? Nope, I should probably be in the liquid phase. I'll probably be solid at 1,000,000 atmospheres, but liquid. Okay? And if I have extremely low pressures, as I get to pressure equals to 0, that's effectively the conditions of an ideal gas, where the ideal gas applies. So at very low pressures, I should expect to be in the vapor phase. Now, I have, in this scenario here, the more volatile species is on the x-axis. Okay, so I'm trying to figure out, compared to, so this one over here, this is 100% B. And at this point right here, it's 100% A. So at some point on this line, I will transition from liquid to vapor. At some point on this line, I will transition from liquid to vapor. Now, if I have a high volatility species, right, it really wants to evaporate. Should it evaporate at a higher pressure or a lower pressure? PXY diagrams are confusing. Everything's opposite. Take your intuition and flip it upside down. A highly volatile species really wants to evaporate, right? So it'll evaporate even at a high pressure, right? So the high volatility species here, this will correspond to P star of species A at the temperature of this phase diagram. Right? So water, for example, will stay a liquid until I lower the pressure down to about 3 kilopascals. But acetone, right, it'll turn into a vapor at a much, much higher pressure, maybe 30 or 40 kilopascals. Right? The more volatile it is, the more you have to squeeze down on it. Now, it'll be a lot more intuitive when we talk about the TXY diagram, because that one makes a bit more sense. We generally don't change the pressure in our everyday lives. We generally change the temperature. Okay, so now this is 100% B. This is the less volatile system. So if I want to make vapor out of the lower volatility system, I have to lower the system pressure a lot more. So this is going to be P star B at whatever the system temperature is. Okay? I'm going to draw the lines of how to connect this, and then we're going to give the equations in just a moment. So as it turns out, for Raoult's law, if I can draw this straight, this line here is straight, this line here is curved. Okay, so we're going to walk through what these two lines mean. Very high pressures, everything should be in a liquid. Very low pressures, everything will be a vapor. What do we call it when we go from a liquid to a vapor or a two-phase region? Could be evaporation, could be boiling, right? So we call this, in vapor-liquid equilibrium, the bubble curve. Okay? Because the liquid starts to form bubbles. In this case, vapor bubbles. Now, what about when we go from vapor to a liquid? Condensation. What happens on a cold morning in spring when the weather's beautiful? Dew, right? The water condenses from the atmosphere because it's a multi-component system, and it forms liquid water droplets. We call that dew. So this is the dew curve. Okay. So this here is the two-phase region. So if I were to run my flash separator for benzene and toluene, if I run this flash separator at a condition where the toluene is a liquid and the benzene is a liquid, I've done a pretty bad job at my separator, right? Because I will feed in a liquid, it'll go into my flash separator, and it'll all just fall down and then go right out of the bottom stream. I have not done my job. Now, if I feed this at a temperature that's too high or a pressure that's too low, and the whole stream is a vapor, well, the vapor will flow in, and it'll flow up, and it'll flow out. And I have not done a good job of my separation because the feed and the outlet are exactly the same. So if I'm operating my flash separator, I need to make sure that I'm at a condition that is in the two-phase region, because then I can have a vapor of one composition and a liquid at a different composition. We have to do that in order to purify the species that we're synthesizing. So the key thing when we're looking at phase diagrams is that at a phase transition, temperature and pressure are constant. Right? They're not equal to each other, but across the phase diagram, the temperature is constant. Across the phase transition, the pressure is constant. So I have drawn this phase diagram at a constant temperature, right? Because it's a PXY diagram. And we're explaining where the X and Y come from in a moment. Now imagine that this plot comes out of the board, and every slice is a different temperature. Okay? I have chosen one slice. So this temperature is already constant. Now, if I want to ensure that the pressure is also constant, how do I figure out what constant pressure looks like on this graph? So horizontal line. Okay, so I'm going to choose some arbitrary horizontal line. And there we go. I now have a constant temperature and a constant pressure. Now go back to middle school or early high school when you're solving systems of equations on your graphing calculator that your parents got angry about because it cost $130. Okay? How do we solve systems of equations graphically? Where are the solutions? The intersections. So I have two. I have two solutions, one here and 1 here. These solutions are going to correspond to these unknowns. So the do curve, right, is when I have all vapor. And then I, let's say, for example, increase the pressure until some liquid starts to form. Now, does this point tell me more about the vapor, or does it tell me more about the liquid? Right? So at this point right here, I have 100% vapor, 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 99.99% vapor. Does this tell me more about the vapor phase or the liquid phase? Vapor phase. So this point right here, if I draw it down, this tells me the mole fraction of species A in the vapor phase. And then correspondingly, mole fraction of species B in the vapor phase is just 1 minus Y of A. So the dew point tells me everything that I need to know about the vapor phase composition. Now let's go to the liquid side. I have 100% liquid, 100% liquid, 100% liquid, 100% liquid, 99.99% liquid. This one obviously tells me about the liquid phase. So then I draw a line down here, and this tells me x of A, and then correspondingly x of B is 1 minus x of A. Okay? Now, if I have a total composition at some point here, that means, actually, let me draw it here. Okay? So then I will draw this line up. So my Z composition is right here. So if I have, for example, in my benzene toluene system, I feed a total composition at a temperature and pressure where I'm in the two-phase region. Okay, so constant temperature is a big slice across this here. Constant pressure is a straight line across. And the total composition is right here. So I have successfully chosen a condition where I'm in the two-phase region. The solution to that system of 6 equations and 6 unknowns is provided to you by this point, and this point. Okay? So we already have figured out that we can determine 4 of our unknowns, yb, yt, xb, xt, right? That's just the intersection of a constant pressure line with the bubble curve that tells us about xa and the dew curve that tells us about y of a. Are we good so far? Yes.
So in the middle region, in the two-phase region, you can't just choose an arbitrary one of those and say this one is the Z of A, it's just the intersections that are the solutions?
So when you're doing this as a chemical engineer, you get to decide all of this,
Okay.
right? So you get to determine what temperature should I operate my flash separator at? What pressure should I operate my flash separator at? What is the composition that I need out of my top stream? What is the composition I need out of the bottom stream? And then it becomes a puzzle or an engineering challenge, right? So this is what you get to design. And then it gets more complicated when it comes to distillation columns. Do you want to use a distillation column? Do you want to use a membrane? Do you want to do a liquid-liquid extraction? Do you want to do adsorption? Right? So once we know about all the tools, then we can choose the one that we want. But for this particular example, I'm just saying that we chose some total feed composition that happens to be in the two-phase region. But if this didn't work out, I would maybe have to change the temperature or pressure to operate this flash separator in a region where it was the two-phase region.
So in any of those arbitrary locations, any total mole fraction, the x of A will always be at the intersection, y of A will be at the intersection as long as you choose.
Correct.
Okay.
But let's say, for example, I had the same total composition, but I tried to operate my flash separator up here, in which case, oh, bad idea, it's all liquid.
Okay.
If I operated it down here, bad idea, it's all vapor. If I changed my if I changed my system pressure, I could go down here and I would have a completely different vapor and liquid composition,
Okay.
right?
So as long as you choose it along that middle segment, the x of
Correct.
A, y of A will always
Yes.
be there. Okay.
Yep. So you can choose to some extent where this point is. And you can do a really bad separation if you're outside of the two-phase region, right? So if I were to go down here, right, I would have substantially different vapor and liquid compositions. I'd have a much more pure liquid stream, but I have a much less pure vapor stream. If I were to go all the way up here, I would have a less pure liquid stream, but a more pure vapor stream. Right? But there's one also consideration. If I'm making a really pure species, I'd want to make a lot of it, right? Because I can sell it. So the last two unknowns that we don't have here are the total amount of vapor and the total amount of liquid. They are also in this phase diagram. So the dew point is where we have almost 100% vapor, just a teeny little bit of liquid droplets. The bubble point is where we have nearly 100% liquid and just a few teeny vapor bubbles. Okay, so the way that I like to think of this is it's a tug of war. Okay? The liquid phase is pulling on the rope, and the vapor phase is pulling on the rope. The more liquid molecules I have, the more they win the tug of war. So in this scenario here, do I have more liquid or more vapor? A lot more liquid. Now, if I were to go to a condition here, right, where my total composition is perfectly on the bubble point line, that means I have effectively 100% liquid in the system. If I were to go to this point right here, right, where my liquid composition would be over here and my vapor composition is close to the total composition, the vapor's winning, right? And I have almost 100% vapor. So the distance between these points right here tell us about how much of each of the phase is there. So in this case here, this distance between the dew point and the actual system compositions, this is proportional to 1 over n of the top. And this point here is proportional to 1 over n of the bottom. And this concept here is called the lever rule. Right? And I can provide the lever rule equation, but right now I think it's easiest just to conceptually figure this out. But I almost never use the lever rule because I don't like remembering equations. If I know the composition of the liquid and I know the composition of the vapor, I can just use my two material balances to figure out the total amount. Yes?
So, sorry, going back a little bit, that point that we picked that's in between
Yes.
the dew point and the bubble point, you drew a line going straight down. Is that line relevant? Or are you
This line is the total composition. So if I operated my flash separator at this system pressure, but my feed total composition was somewhere over here, I wouldn't have done a very successful job at doing my separation because it would all be in the liquid phase. And let's go back to the benzene and toluene example. Okay, so in the benzene and toluene example, okay, benzene, right, wants to be in the vapor phase. Toluene wants to be in the liquid phase. Okay? So if I were to go back here, this is 100% toluene on this line right here, even though it says B, so it's confusing, right? So in that example, this is all benzene, 100% benzene, sorry, 100% toluene, 100% benzene. The way that we can think about it is if we're down over here, that means we've got a lot of toluene and a little benzene. This means that all of that vapor benzene can dissolve in the liquid toluene. Right? So you know how you can dissolve carbon dioxide to form carbonic acid inside of a can of Coca-Cola. Okay? As soon as you open, you lower the pressure. Then you now have a supersaturated carbonic acid solution and it bubbles. So your closed can of Coke is somewhere up here. Then once you lower the pressure by opening it, you get into the two-phase region and bubbles start to form. Same concept applies when you have the benzene and toluene mixture. Liquid toluene can dissolve a certain amount of benzene vapor. Same idea applies if I have sugar dissolved in water, right? Just because I add sugar to water doesn't mean I have to form sugar crystals. That water can dissolve the sugar. So when I'm in this region over here, right, and I've changed my total composition, this limit tells me how much of the benzene can I dissolve inside of my toluene. But if I add too much, well, then the benzene can't handle that much, the toluene can't handle that much benzene dissolved, and then you get the two-phase region. So all of these concepts are linked together for phase equilibrium. Yes?
What is proportional to 1 over the moles of benzene?
That's
what value is
the length of the line segment.
Okay.
So the length of the line segment. So
And
for
is that length a relative length to the total length?
correct.
Okay.
Yep. And I'll provide the equation, but right now I just want to go over the concepts of what's contained within there. Yes.
So two things. What exactly is the difference between X of A and Y of A?
So X of A is the liquid amount of A. So this is the mole fraction of A in the liquid phase. Y sub A is the mole fraction of A in the vapor phase. And these values should be different if you're trying to do a successful separation. Because if they're the same, did you really purify your components at all? Right? So if I do a chemical reaction to synthesize toluene from benzene, does the person who buys my toluene really want it to be like 50-50 toluene and benzene? No, they want it to be toluene to a 99.99% purity. Otherwise, it's going to screw up their chemical reaction in the lab. And then grad students are going to be very upset. Right? So once we synthesize the component, we can't just sell a gobbledygook product. We need to purify it. So we must design our separations to get the product to the purity that we need it to get to. Okay, we're going to do the TXY diagram. How do we feel about this so far?
Yeah, I just have a question.
Yes.
So basically, if I'm understanding this right, the points intersections are, the intersection is limits, right? A feed can be anywhere on that line if it's like,
You can feed it at any conditions you want. But if you want to do a successful separation, you have to feed it in between the bubble point and the dew point for the given total composition.
so I was saying in terms of on the graph, like
Yeah.
if you're feeding it at the temperature of the graph set at the pressure that line is.
Yes.
The,
You could still be at a total composition that's totally off base, right? So you could feed it at a total composition where it's all liquid or a total composition where it's all vapor.
the composition of the feed determines the point of the line.
The composition of the feed determines where we draw a vertical line. So the pressure, a constant pressure, is a horizontal line. Constant feed composition is a vertical line.
Well, yes, I'm just saying
Yeah.
if all the points are correct, then okay, never mind. I think I get what you mean.
We can chat more. Yes.
So about the diagram itself, are the bubble curves and the dew curves empirically found, or are they just kind of derived from other equations? Because I can't imagine that, like, if they were empirically derived, we'd be able to do this for a lot of different mixtures, right?
Great question. So maybe instead of the TXY, maybe we'll hit the TXY diagram on Friday, and let's actually go through how do we derive these equations. So back in the old days, we didn't necessarily have Raoult's law. And for most fluids, Raoult's law isn't appropriate. So back in the old days, we would measure this. And actually, we still do measure this, right? Companies pay hundreds of thousands of dollars to get phase diagrams produced for the chemicals that they're synthesizing. And what they do is they go in the lab, and they basically change the temperature and pressure until you get two phases. They take a sample of the vapor, they take a sample of the liquid, they measure the composition of each of those phases, and that gives me 2 data points. And then they repeat it at a different temperature and pressure. And then they repeat it again at a different temperature pressure. And then they build up a series of data points, and they connect the dots. And multi-phase thermodynamics is how we figure out how to derive equations so we don't have to make those measurements anymore because they're very expensive. You all will be able to do these calculations that save hundreds of thousands of dollars. These are really tricky experiments to do. So we're going to go with the bubble point first of all. Okay, so the bubble point is going to be very important that we have a super specific assumption. Okay? That specific assumption is that the total composition, Z of I, for all the species, is approximately equal to the liquid composition. This is the magic of the bubble point, is we're making an assumption that the total composition is equal to the liquid phase composition. So what we have is mole fraction of species I multiplied by the pressure is equal to mole fraction in the liquid phase times by the vapor pressure, and I'm leaving the little t in here. Now, when we're doing algebraic derivations, there's usually a good counterintuitive approach. It is start with the equation where we know nothing, and then substitute stuff into that equation that we do know. Okay? So if I know that the total composition is equal to my liquid composition, I know the least amount about my vapor phase. So I'm going to start off with the equation that the summation of the mole fractions in the vapor phase equals 1. So I can take my Raoult's law now, and I can actually rearrange it to solve for y of I. Now, I'm doing this generally. For a two-component system, this would, of course, be ya plus yb equals this, and this would have a, and b, b, b. Okay? But I'm solving this just generally because the derivation is really quite trivial. Okay, so I'm just going to rearrange my Raoult's law here such that y of I is equal to the liquid phase mole fraction multiplied by the vapor pressure divided by the system pressure. I'm then going to substitute it into my thermodynamic consistency relationship here, which is that the mole fractions have to add up to 1. I'm going to combine these together, and I'm going to get that 1 is equal to the summation of x vapor pressure over p. And then I can pretty easily solve for p because it's constant. So that means I get p, in this case, is p bubble, is equal to the summation of the mole fractions times by the vapor pressure. Let's go back to our pxy diagram. This formula here. Is this a linear or nonlinear equation? Linear, right? Because I could just plug in values, right? So if I have a 50-50 mixture, it's 0.5 times by the vapor pressure, 0.5 times by the vapor pressure. If I do a 25-75, it's 0.25 times the vapor pressure plus 0.75 times the vapor pressure. So that's just a weighted average of the vapor pressures. And if we look at our phase diagram, well, indeed, my bubble curve is just a straight line connecting the vapor pressures. It's just a weighted average. That's what Raoult's law will produce. Okay? So when I make a phase diagram, all that I'm doing is for a given pressure or a given total composition, I'm just solving for the unknowns. Right? So if I just make mixtures at all a bunch of different compositions along this line, okay, I'm just varying the mole fractions, and I'm solving for the pressure, and I'm plotting those lines together. And that's how we get the bubble curve. Okay? Now, if I were to flip this around and to do this for the bubble temperature, I would have a fixed pressure, and I would have a nonlinear equation where I'd have to solve for at what temperature do the vapor pressures of the species in the system add up so that is the total system pressure. So it's the same equation that we're going to use for temperature diagrams versus pressure diagrams, but for pressure, it's linear, and you can just plug and chug. For temperature, it's nonlinear. Okay, now let's do the do curve really quick. It's going to be the same idea. The only change is that in this case, the total composition is going to be approximately equal to the vapor composition, because we're assuming it's going to be almost 100% vapor. So I'm going to do exactly the same thing, but instead, I'm going to start off on the opposite, and all of my unknowns are contained in my liquid phase. So I'm going to rearrange my Raoult's law such that I can solve for xi, so I can substitute it into this equation. It's going to be yi times by p divided by the vapor pressure. I'm going to substitute it into this equation here, such that I get 1 is equal to the summation of, let's see here, y I p over p I star. Now this one's not quite as straightforward because I can factor out the pressure and then divide this to the other side of the equation. So my dew curve, P equals P dew, is going to be equal to 1 over the summation of mole fraction divided by the vapor pressure. Okay. Is this a linear curve? No, this is nonlinear. And look, the dew curve is a nonlinear equation as well. Same idea holds true. I plug in a bunch of different values of y, and I can solve for what the pressure is. Now, these equations, well, one second. So these equations here are actually generally applicable. Right? So all flash calculations, you can use this equation and you can use this equation, regardless if you're at the dew point or not. Because I didn't make any assumptions in the algebra. I made one assumption. This is the main assumption. If you assume that the total composition is equal to the liquid composition, or the total composition is equal to the vapor composition, that's how we get the dew in the bubble curve. But everything below this assumption is totally valid for your flash calculations. So when you're working through how to solve these systems of equations, you can actually just jump start in on one of these two equations and be totally okay. The only thing that makes these dews and bubble curves is this assumption here. But this equation, right, is only the bubble point if x is equal to z. Does that make sense? Okay, we had a question here.
Yeah, so if on the diagram we set a constant t, if the t is constant and the percent of the t, could we not factor out the critical pressure?
So in a pxy diagram, we're going to fix the temperature. Once we fix the temperature, we can look up the vapor pressure using Anton's equation or some other chart. And this becomes a really easy calculation. It's plug and chug, right? We can't factor it out, no. So it's just based on, if we were to draw this out algebraically, so this would be P is equal to 1 over y of A over P star of A of T plus y of B over P B. On the bubble curve, we can't do that either, because in the bubble curve, it would be so the difference is that P A star and P B star are not the same thing. It's two different components. Yeah, so we can't factor it out this way. Okay. All right, quiz on Friday, and we're going to continue to talk about phase equilibrium.